Comparing unlike events can be really difficult, especially when they have different means and standard deviations, kind of like they have different expected values and different variabilities, so how can we compare them? So something we do is we standardize them. We create a ruler using the standard deviation. So what we do is we calculate how many standard deviations away was a certain event. So how far from expected was it compared to the mean? So what we end up doing is we create this ruler, and so we end up with a number line that kind of focuses on this middle of 0, and we could go 1, 2, and then -1, -2, such that if you land at 0, that would be the idea of being at the mean. So this idea of being 0 standard deviations away from the mean. If you land at +1, that's the idea of being 1 standard deviation above the mean. And if you land at -1, that would be the idea of being 1 standard deviation below the mean. So we end up with this number line that tells us location based on standard deviations away from the mean. And we go positive and negative with it. But by putting everything on the same number line, we can compare two unlike events. So what we're going to do is compare Portland rainfall with Chicago wind speed. So as these have different units to them, and then different expected values, different standard deviations, they behave very differently, so it's hard to compare them directly. So with Portland rainfall, they tell us that we have a mean of 40 and a standard deviation of 8. And with Chicago wind speed, we have a mean of 10 miles per hour, standard deviation of 2 miles per hour. And what we want to do is compare that Portland had annual rainfall of only 24 inches, so something that was very below average one year, and Chicago had an average wind speed of 13 miles per hour, so something that was above average. But we can't compare these yet because of different units. Also, there's this idea of each value has a certain expected value and certain variability to it. So to compare which was more extraordinary, which in terms of comparing extraordinariness, what we're really looking for is which of these events is furthest from expected. Or instead of expected, you could think of which is furthest from the mean or furthest from average. So what we do is we calculate something called a z-score. So this is our formula for z-scores. We calculate this number z, and we take this value x, which is going to be some data value, minus the mean. So what we're doing in the numerator here is we're creating this distance between a value and the mean. And what you'll notice is it technically isn't a distance because we're going to have positive and negative coming out. And what's going to happen is if it's positive, that tells us that we're above average, to have a positive number come through. And we don't really need to worry about the denominator here because that's our standard deviation. And standard deviation's always positive. So it's in the numerator that tells us whether we have positive or negative. And if it's positive, that means x is big and the mean is small. So if our z-score is positive, we are above average. That value is larger than average. If it comes out to be exactly 0, so if we subtract our two numbers and get 0 out, well, that means our data value is exactly the same as the mean. So we are exactly average when that happens, which links to the number line that I drew up above here. At 0 is where we're at the mean. Anything to the left-hand side would be below the mean. And sorry, that's our next one here. So if z is negative, that is below average. And then on that number line where we have positive numbers coming out to the right-hand side, that's the idea of above average. So we get this idea of where we're landing in terms of above or below, and we get this distance in terms of standard deviations. So we take this distance from the mean, we divide by standard deviation so that that becomes our units for that distance. So let's see how to use this formula for this case of Portland and Chicago. So with the 24 inches of rainfall, how the formula would go is calculating Z. 24, that's our data value that we want to compare to the mean and standard deviation that we have above. So we want to take that 24 minus that mean of 40 and divide by standard deviation of 8. And that would give us this Z equals -2. So what that's telling us is 24 inches of rainfall in Portland is, and this is giving us our distance away from the mean in standard deviations. Now because it's negative, that means we're below average here. So this is 2 standard deviations below average. So it gives us this idea of where we're landing and how far away we're landing. Then with Chicago wind speed, where x is now going to be 13, so calculating z, we're going to take 13 minus our mean of 10, divided by that standard deviation of 2, and this is going to be 1.5. So that 13 mile per hour winds in Chicago is, and this is going to be above average by 1.5 standard deviations. So 1.5 standard deviations above average. So now what we have here are these numbers that we can compare on the same number line. So what we can do is draw that number line where 0 is our mean, then go 1, 2, 3, and -1, -2, -3. And in terms of Portland landing at -2, you can see that we're landing here at -2. There's Portland, and Chicago was at positive 1.5. So here we are with Chicago. And if the idea of being at the mean is at 0, we want to see which is further from expected. So which is further from 0? Well, in terms of distance, Chicago's 1.5, but Portland is a distance of 2 away, which means it was a more extreme value happening below average. So Portland was more extraordinary since it was further from 0, is what's happening here. Further from 0, further from the mean is how we would translate that. And actually landing at -2, remember in terms of the empirical rule, what we talked about was being at 2 standard deviations away or more. Anything out there is considered unusual. This rainfall of 24, that would actually be considered an unusual event because of that z-score of -2. So if you have a z-score of -2 or less, or +2 or more, those are considered unusual events. Something that happens with this number line, and it's kind of happening separately with these two cases, these are normally distributed events, so that they have these 2 separate number lines. This one is centered at 40, and then is using standard deviations of 8. This one's centered at 10, using standard deviations of 2. So we have these 2 totally different number lines, but what we do is we get to combine them onto this single number line. And the idea being, for these events, and for when we get to this distribution here, it's that at 0, there's a high likelihood. And there's a high likelihood of being just 1 standard deviation away. And then as we get further and further away, it becomes less and less likely. And that description right there is our bell-shaped curve. So we're going to see this bell-shaped curve that has this number line of 0 and then these jumps of 1, basically using units of 1. And this is called our standard normal curve. And this standard normal curve is special because these numbers along the number line here at the bottom, those are all z-scores. So it's going to be this curve specific to mapping z-scores, where we'll always have 0 in the middle and using these units of 1. So let's talk more about that. So standardizing into z-scores does not change the shape, so we're still going to have this bell-shaped curve coming through. We're going to have a mean of 0, so there's our mean, and spread standard deviation of 1. So normal distribution model tells us bell-shaped curve. That's what that translates to. It's a continuous distribution, meaning we can land anywhere on our number line. Then we're going to have these two terms. There's normal model, and then there is standard normal model. And you want to be careful of if it says standard normal versus normal, because normal is a distribution of x values. We have a normal curve defined by some mean, some standard deviation. We would need to be told from the wording of the question what that mean and standard deviation is. If we see standard normal, that's a distribution of z-scores. It always relates to z-scores. And with that, we have a normal distribution with a mean of 0, standard deviation of 1. Every single time. Every single time we want to work with z-scores, that's our distribution. And to calculate z-scores, we have our formula right there. So if we need that standard normal curve, bell-shaped curve, and then we get our number line using 0 in the middle, and then jumps of 1 to make our number line. What we can do is calculate probabilities with this curve, just like we did in other scenarios. What we could do is look for, let's say we were interested in the probability of z less than or equal to negative 0.3. Well, if I just saw this notation right here, probability of, and then I'm using z, when I'm in GeoGebra, this is telling me immediately that I need to use this distribution. Mean of 0, standard deviation of 1. As soon as z is in the notation for finding my probability, mean of 0, standard deviation of 1. So with that, we go to GeoGebra. And when you go to GeoGebra and open up probability, what you'll notice is this standard normal curve is always what automatically comes up. Mean of 0, standard deviation of 1 right there. And it's because this is the most commonly used curve, and pretty much you can make z-scores out of all of the scenarios that we've calculated probabilities with. And it's just as good, but it can be extra work. So with that, you can always edit the mean and standard deviation to make the normal curve that fits the scenario, or you can find the z-score and always use this standard normal curve. So this finding z less than or equal to negative 0.3, we can go less than or equal to, edit that negative 0.3, and get out that need 0.3, 0.3821. And let's say I asked for the probability of negative 1 is less than or equal to z is less than or equal to positive 2. Again, seeing this notation, we'd have to have mean of 0, standard deviation of 1. So without any other context, that would be the scenario. So going to GeoGebra, looking between two values, negative 1 up to positive 2 is a 0.8186. So we can use this curve to find probabilities. You can also work with percentiles with it. It's just always relating to z-scores. Let's look at this last example together. We have an incoming freshman, took a French test and a math test. So let's collect the information for these two scenarios. For the French test, she scored an 82. And for the math test, she scored an 86. So for the French exam, there's a mean of 72 with a standard deviation of 8. And then with the math test, there's a mean of 68 with a standard deviation of 12. And we want to see which exam did she do better on. Now notice with extraordinary, it was just about distance away from the mean. In terms of better, we definitely want z to be positive here because we want to be above average with these test scores. So if we got a negative value out, that would actually mean they did really badly on the test, so it wouldn't work out. So let's just compare it at this point. We have these numbers. I mean, comparing 82 to 86, it looks like that math score is better, but something we need to take into account are, first we can start with the averages, which the French test has a higher average, so that doesn't necessarily make that 82 any stronger, whereas the math test actually has a very low value compared to what she scored. So just comparing that, it looks like this math score is going to win because it's so far away. However, something to take into account is the variability, and the French test has less variability. So that means that being far away, like 82 compared to 72, having that distance actually means more because there's less variability, meaning you really expect to be close to 72. Whereas with the math test, like, yeah, we expect to be at 68, but there's a lot of variability, so being far away doesn't mean as much. So that's where just comparing the numbers, just comparing the means isn't good enough. You also have to think about standard deviation. So we need z-scores. So the z-score for the French test, we're going to take that 82 minus 72 and divide that by 8, and that'll give us a 1.25. Oops, and my pen stopped working there. I'll fill this in. We're almost at the end here. And then for the math test, the z-score would be 86 minus 68. Divide that by 12, and that would be a 1.5. So with that, thinking about distance away from the mean, that 1.5 is further above, which would mean that score is better. Sorry about my pen failing at the end here, but I'll fill in the completed notes with the accurate results there. Thanks.